Well, hello, this is Professor Needing, and we're going to be starting another tantalizing visit into statistics, and we're going to start actually the end of chapter 6 for us. So I'm going to bring up this, and you have to excuse me, I'm trying to hide the webcam application that I have going on here. Sometimes it likes to come in and it likes to come out. I don't know what to tell you. Let me see if I can just shrink it back a little bit. There we go. So we're going to talk about, and let me back up, sorry. In chapter 6, we're going to look at going from generating stat key for everything we do to actually doing what we refer to as the theoretical formulas of the mathematics. And the reason I have this window open over and left, my webcam, I got it opened up to my formula sheet that we've used so often. Okay. And remember, this is inside of Canvas for you, and you'll have access to this when you're doing any calculations. And we're going to want to have this today. I have this in not only the written format, but I have it also in a digital format. We're going to go back to a couple times. So I'm going to hide it off to the side for right now. And you'll notice that the chapters don't actually sync themselves in what we refer to as, proper order. We're going to go from chapter 6.1, which is a single proportion, to chapter 6.3, which is the difference of proportions, to 6.2, goes back to a single mean, and then 6.4 jumps to a difference of mean. The book's a little out of order, we feel, and we prefer to teach it in this particular order. So let's talk about 6.1. In 6.1, we're going to calculate the standard error for a sample proportion. And remember, standard error is the amount of movement from a central location. And then we're going to discuss the central limit theorem, sample sizes for central limit theorem, CLT. And we're going to talk about the CLT for a sample proportion. So we'll actually calculate the central limit theorem, and we'll also do some calculations of standard error. When we distribute a value of p hat, any statistic, we are basing the knowledge of, or the view that we see of that distribution, on the size of the samples. And we've seen this in the past to where as we grow the n value, we get a much clearer picture. One or two samples don't give us a clear picture. Hundreds and thousands of samples give us a clear picture. And we can kind of see that take place here. If we truly have a p hat value of 0.5 and we take one sample, well, I could have a 0 or I could have a 1. I had a 50-50 chance, heads, tails, yes, no, something like that. So either I got it right or I got it wrong, one of the two, if my chances were truly 0.5. But if I do n sample 10 times instead, now I start to see a much truer picture of that center, if you will, of 0.5. That p hat value becomes much more prevalent in the center of my problem. As I do 30, it shrinks in. Notice that we're getting a smaller standard error. Remember, the standard error is from the center moving in edges to the left and to the right. I'll get myself a pen here so I can do a little bit of drawing, and we can have that discussion here. When we look at this, you can see that the sample itself, its standard error, is shrinking as I increase n. If I increase n more and I increase n more, there's a dramatic change between how wide the data gets from the true center and how much it moves out by. Remember, when we move items out, it's the value, some center, right? Some mu value, some p value, some value, plus or minus two standard errors. And that's what we're seeing in this distribution. If we had a 0.7, again, I don't know what I got. I was supposed to get a 0.7. Maybe I got a 0, maybe I got a 1. But as I do more and more and more and more, we see that true center. Again, larger sample size creates a smaller standard error. That's what you want to take away from this slide. P-value of 0.1, well, we know the center should be at 0.1 and everything should be hovering around 0.1. And I start to see that a little more and a little more, much better, and I start to see that really nicely. We'll see how this effect plays upon the formulas that we utilize shortly. So let's talk central limit theorem quickly. The central limit theorem says when the sample size is large enough, so it's a very ambiguous term to begin with, distribution of a sample proportion is approximately normally distributed in the center at the value of the population parameter. We just saw that. If you give me enough n values, I'll be able to approximate the population parameter, which is the center, and I'll be able to tell you approximately what the normal distribution is or the standard error. When doing the inference of proportions, we approximate the distribution of a sample proportion with a normal distribution, provided that the sample is large enough. Okay, well, what does large enough mean? In our terms of large enough means that the number of n, when multiplied against the proportion of that n, will be greater than or equal to 10. And at the same time, the number of n multiplied by the counterpart, or the 1 minus the proportion of the other group. So this is the first group and this is the second group, will also be greater than or equal to 10. We'll do that calculation in a second. It's a straight, easy calculation. We multiply two numbers together, and we're looking for numbers bigger than 10. This is the actual formula for the central limit theorem. And I bring it up now because I want you to know that you don't have to remember these things, that you will have them to you. And I'll bring back up again the formula sheet, and you can look into the formula sheet and you can see, first of all, I have this thing called the standard error. And the standard error says square root of p times 1 minus p divided by n. And it's in single proportion, and it's right here. I also have these conditions that say, hey, if you take n times p, if they're greater than or equal to 10, and if you take n times 1 minus p and it's greater or equal to 10, then you have met the conditions for a single proportion. Well, I bring that up because that's exactly the formula we're talking about here. The formula we're speaking about is right here. So the formula, or the central limit theorem, says that we can normally distribute values if, one, we know some p-value, p-hat value, I should say. Got to get myself a color here. How about maybe red? Some p-hat value. We will normally distribute that p-hat value with a center p as our population parameter, and we will normally distribute it, comma, over its standard error. This calculation above is our standard error calculation. But it also goes on to say that it has to be normally distributed with a good approximate as long as np is greater than 10 and n times 1 minus p is greater than or equal to 10. So we need to actually do that. Now, there is a small problem, okay? Remember that this p-value stands for the population parameter. This value right here is the population parameter. Well, we don't know the population parameter because we have a sample. So in our estimation, the best thing that we can possibly do is we can use what we call the best point estimate. Okay, and you've heard those words before down here. Best point estimate. The best point estimate is the sample statistic that we have. It's p-hat. So we are going to replace in our formulas a p-value that we don't know with a p-hat value. We're going to use the best estimate that we have going on. So we have this question in Wiley. And this question in Wiley says that in each case below, is the sample size large enough so that the sample proportion follows a normal distribution? Okay. So I'm going to bring the screen over here so I can do it. It's easier for me to write over here than it is for me to write on the screen. And at least it's a little neater for you, I hope. All right. So first things first. So we're going to check both of these. And our first given value, and remember our formulas here are one, that n multiplied by p has to be greater than or equal to 10. And at the same time, n times 1 minus p has to be greater than or equal to 10. Okay, so our first set of n, 550. Our first proportion, 0.15. And our first question becomes, okay, is that greater than or equal to 10? All right, well, take a calculator, do the math, crank that number out, and I get 82.5. 82.5. And so my first question is 82.5 greater than or equal to 10? And the answer to that is yes. I'm halfway there. Not only does this one have to meet the parameter, but this one has to meet the parameter also. So for my second one, I'm going to take the same n, because the group size did not change. I'm going to do 1 minus 0.15, because this is the other proportion. So one of the proportions is 0.15 or 15%, and the other one is really 85%. I'm going to take these numbers and multiply them, and again, I'm calculating to see if it's greater than or equal to 10. When you do the math for that, if this 15% of 550 was big enough, then 85% of 550 is definitely big enough. However, though, the math says 467.5. Definitely greater than or equal to 10. Answer is definitely yes. We're going to mark ourselves down for a yes value for this first answer. That's an awesome filling in of that circle, wasn't it? Okay, I would encourage you to stall me for a second, shut me up, and go give yourself a try with your next one. Okay, hopefully you've tried that and you've come back and let's see what your answer is. So I'm going to take the first set, and I'm not going to do the formulas again. They're right here. So my first set is 30. I'm going to take 30. I'm going to multiply it by the proportion, 0.3. I'm going to search out if that's greater than or equal to 10. I'm also going to do 30. I'm going to multiply by 1 minus 0.3, 70. And I'm searching to see if that's greater than or equal to 10. Those are my two CLT confirmations for is this n value large enough. Well, when you do this one here, 30% of this is 9. 9 is not greater than or equal to 10. I immediately get a no. I don't even really need to waste my time going over here. If I did the math over here, 21, this would be 21, because remember, this 9 and this 21 have to make this 30. This would be a yes. However, one single no, we don't care that the other side is a yes. So my second value, or my second part of my question answer, is going to be no. A single no value, if you don't have a sample size which is large enough, then you don't meet the requirements of the central limit theorem. Now, does that mean we can't compute the math? No, it does not. What it means is that our distribution will not be normal and we can't trust what we're seeing. I'm going to move myself a little bit here so I am out of the way. So a couple of things here. What? It says use stack keyword technology to generate a bootstrap distribution sample of the proportions to find the standard error for the distribution. Compare the results to the standard error in the central limit theorem. So, okay, so we've got to do two things here. First thing we have to do is we have to go off and use StatKey, and we need to do a bootstrap SE for an n value of 42 with a p hat value of 0.42. We will do that first. So give me a second to exit here. Discard my stuff. Go find my values here. Go find StatKey, and here we go. StatKey. Okay. Now we could do a CI here because we want to see a standard error, but I'm going to use this right here. Sampling distribution. This is a nice one. I'm going to go to a proportion because it's a single proportion. In that single proportion, I can choose to change my n value right here. My n value for that question was 42. Then I'm going to change the proportion, not the data, but the proportion. And the proportion was 0.422. From there, I'm going to run 1,000 samples, and I'm going to focus my attention right here. 0.77 or 0.077. That is my standard error. And that's what that question was asking of me, is what is the bootstrap standard error. Okay, so I'm going to write that down at 0.77. That's what we'll start this problem at. So we did bootstrap. Awesome. We did good job. 0. And there was a 0 in there. 77. Okay. Now we're going to use the actual formula itself. Okay, so back over to here. And from here, we're going to do some calculating. I'm going to flip mine over. So now we are going to go into our formula sheet, and we're going to utilize the standard error formula right here. Okay, and I'm doing that because I'm in a single proportion. I'm not calculating conditions. I'm calculating standard error. Okay, so SE equals this value right here. So I'm going to utilize the standard error formula to be the square root of P, but remember, we're using P hat because we don't know P, 1 minus P hat, all divided by root of n. In my particular values, I have to go find my numbers here and see where I am. I have 0.422. That was my P hat value. Times 1 minus 0.422. All divided by an n value, and my n value was 42. Go plug that in your calculator. And I think when you get your calculator warmed up, you get a I got 0.76. What we were doing was we were confirming that if we utilize technology, StatKey, and if we do the calculations manually by ourselves, that we will get similar results. Because remember, if we ran this in StatKey all over again, we would get something that isn't quite exactly the same. 0.76. And these two things should be very close to each other. And they are very close to each other. They're close enough that there would be no change in whatever decision process we were making. Okay? I would much rather all day long run the formula myself than go to StatKey. I just feel more confident about what I'm doing. Okay, let's go to the next one. And let's skip the next one. And I'm going to move this slide out of our way again. I tend to be in our way right there. So let's talk about a confidence interval for proportion. It says that the best point estimate, that's a p-hat value, also known as the best point estimate, also known as the sample statistic. All of these different analogies here talk about the statistic. To calculate a confidence interval for proportion, we're going to take the statistic and we are going to plus and minus it against the z number. And remember, we already know where to find z at, z star. And we're going to multiply that by the standard error. Well, now we actually know how to find a standard error. Okay, so we can take these values and we can calculate them manually by ourselves. Okay, and again, we're doing a CI here for a proportion. So that's important that we look at that. And then I also want to bring your attention back to, real quick, your formula sheet. And remember, on your formula sheet, general formula, confidence interval, sample statistic, plus and minus z star, and z star gets multiplied by the standard error. And remember, right above it are your z star values for your common 90%, 95%, and 99%. They're right here. 2.576, 1.96, 1.645. If we have to calculate those on our own, we can certainly do that. So let's return and let's see what we can do. And remember, all of this is in reference to us having an n value which is large enough. So we may have to make sure that we check that. Now, it says that if we take this one step further, that if we know p hat, that's our statistic right here. Statistic is p hat. if we plus and minus z star, right here, z star, and if we remove the standard error terminology and use the formula that we just used a second ago, that we can actually make the confidence interval using this straight formula right here. And again, that's on your formula sheet also. And when we make that valuation, we'll be able to get this confidence interval of going much quicker. It says the z value is the normal cutoff, and we know that. It says a TI calculator, to do this, we use the inverse norm area to the left, and the z table is given on the formula sheet. Okay, well, I showed you on the formula sheet where a couple of them were. And I showed you, for instance, the 99%. I showed you the 90. Sorry, I have to keep moving around on you guys like this. You might feel dizzy by the time all this is over with. This is our 90, this is our 95, this is our 99. And I'm just going to run that on a calculator so you can see how that works. So let's say that I want to calculate an error, or I want to calculate a confidence interval level. So when I'm looking at a confidence interval, I use an inverse norm. Okay, second inverse norm. And I do an inverse norm value. Now, let's say I want to calculate area. Okay, well, on a 90%, remember a 90% is a two-tailed test with 5% on each side. So let's say I'm going to do a 5% left-hand side test. And I'm looking to get this number, this 1.645. So my area would be 0.05. That's 5%, right? That's half of 90 split up in two sides. Always a 0, always a 1, always a left tail. And I hit the button, and boom, there's my 1.645. Remember, there's always a negative and there's always a positive. So if you needed to get one for, let's say, a 92% test, and a 92% test means 4% on each side, you would use the inverse norm. You would use 4% because that's one of your tails. You would always leave a 0 and always a 1 and always a left. And your number that you're going to calculate with is 1.76 when rounded. Okay, that's how you get a z value if you're not given a z value on a chart. So let's scooch over to the next question, or the next slide, I should say. Use the normal distribution to find the confidence interval for proportion P, given that the relevant information is here. We're going to use a 99% confidence interval, and our P hat is given to 0.4, and our N value is given to be 475. Okay, so a couple of things here, first of all. Let me drag this over here because we're going to need this. I'm going to need to do a little writing here. We're going to be using our formula, and our formula is going to come from right here. Single proportion, confidence interval, P hat plus or minus Z star plus the root of, we know this to be our standard error now. Okay, so I'm going to move that off to the side. I don't need that. I need to, first of all, recognize what the best point estimate is. Okay, well, the best point estimate, remember, was the value that I was given in the problem. And the value I was given in the problem was 0.4. So my best point estimate value should be recorded in my problem here as 0.14. I'm going to change my color, get something a little bit better right there, and 0.4. And that comes from right here, p hat. That's my best point estimate. Now, my margin of error. Remember that my margin of error calculation has to come from two standard errors. Okay, my margin of error is going to come from two standard errors. So I'm going to go off to the side. We're going to actually make this calculation happen. So our margin of error is going to come from our formula. And our formula says that instead of taking 2 times the standard error, we can just simply calculate Z star. This will be much more accurate. Multiplied by P hat times 1 minus P hat. And we're dividing that by N. Again, we are replacing 2 standard errors with the margin of error being equal to Z star times the root of p hat and 1 minus p hat divided by n. So let's go fill in our values that we know for this problem. We know z star from the formula sheet. And again, go to the formula sheet, 99% right here, 2.576. So we're going to use 2.576. We're going to multiply that times the square root p hat. Well, remember our p hat value given was 0.4. Multiplied by 1 minus 0.4. All divided by n, and our n value was 475. Push the buttons on your calculator. 0.58. So we now know that we have a margin of error. Instead of using two standard errors, we now have calculated the true value at 0.058. So the 99% confidence interval level. Okay, well then, in order to get the confidence interval level, we're going to take the original statistic, 0.4. We're going to plus and minus a margin of error, and the margin of error is 0.058. If we do that math, 0.342 and 0.458. And I'll let you write those in for the two boxes on the left-hand side screen. Again, we're doing all the same calculations that normally would have been done for us in StatKey, but we're finding those on our own at this particular time. I'll shrink this down, move it over, and let's continue. So the margin of error. We're calculating this margin of error based on the z-star value being multiplied against the p hat and 1 minus the p hat to get n. Now, if we did a little bit of math on here, and I'm not going to go through the painstaking part of it for you of doing the algebra, let's say that we want to find n. We're not looking for the ME, we're looking for n. How many n's do we have to have if we want to hold a certain margin of error? Well, if we do the math on it, then n would be equal to z star divided by the margin of error, because that's the movement, is the margin of error, and we would square that value. Okay, it's the algebra which takes place. And if we look at our formula and we take a look at some things, I'm going to bring you over too. And I'm going to open this back up for you. Oops, sorry. Take a look right here. Estimate the sample size for a proportion, and here's our formula, the one we're talking about right now. We're going to take z star, we're going to divide it by ME, we're going to square it, we're going to multiply it by whatever p hat is times 1 minus p hat. And we're going to get the estimation for how big should the sample size have to be. Okay, so let's go do a problem like that, I think. Again, though, here we go. It says we haven't seen a sample yet, so we don't have the value for p hat. Okay, so we don't know an n value here because we haven't even grabbed a sample. We want to know, hey, how many people do I need to go ask if you want me to do this question properly? So we don't even have a p hat statistic. So the value we are going to use is we're going to say, hey, you know what? Flip a coin, true proportion both ways, that p is going to be equal to 0.5. And the reason we're using 0.5 is because it's even. It's even in a proportion. It's dead center for a proportional value. So notice the tilde above here. The tilde is the proportion that we are utilizing on a best guess, if you will. Let's try that. It says we examine the effects of different outputs to determine the sample size needed to obtain a specific margin of error. Finding the sample size needed to give a margin of error estimate proportion within plus or minus 2%. Okay, so the first thing is we're calculating based on 2%. With a 99%, a 95%, and a 90% confidence. Assume no prior knowledge about the population proportion P. Okay, so we don't need to worry about any values there. Okay, so we are going to need a couple of things here. First of all, we're going to have to, and I'm going to have to blow this up so we can do a little bit of writing over here again. We're going to have to recognize the fact that our z levels are here. Okay, so these are our z levels, and we're going to use this particular formula right here. Okay, so use your references. I'm going to move mine off to the side. So let's do the very first one. So let's take a, first of all, since we're doing a 99%, Z star for a 99.99% is 2.576. 2.576. That comes from the formula sheet. We're going to need that. Okay. So we're going to take the formula, 2.576. We're going to divide that value by 0.02. 0.02 was my measurement of error. Remember in the formula, it says it's a 2% measurement of error, and the decimal equivalency for 2% is 0.02. So that's why that goes here, because remember, we divide by the margin of error. We're going to square that value, and then we're going to multiply it by p hat. Okay, well, we're going to multiply. I hate to use that x for p for x, but I'm going to use it right now. We're going to multiply it by p hat, which is 0.5. Remember that best guess going on kind of thing. And then 1 minus 0.5. Put this in your calculator. And when you put that in your calculator, you're going to get out 4,148. 4,148. I'm going to stall my video for 1 second so I can actually put that in and show you what that looks like when you stall that, or when you put that into the calculator. Hard. Give me 1 second. I'm going to stop my video. I'm going to open it up, and then I'm going to be able to move right along. Okay, so I'm back with you, and here's my calculator. And so first thing I'm going to do is put in a fraction. And I'm going to put in 2.576. I'm going to divide that by the margin of error, which is going to be 0.02. Okay, and I actually want to insert a parenthesis here, and I want to go back over here. I should have opened one, and I'm going to put one in here. There we go. I'm going to scoot myself over again. And I'm going to square this thing. Okay, and then I'm going to multiply by, and you don't have to hit multiply, but it's not a bad idea. 0.5 and 1 minus 0.5, which, yes, we all know is 0.5 all over again, and we hit the button. Oops, sorry. And then we hit the button, and then we see that Kneading made a mistake when he did this because he didn't put in 1 minus 0.5 up here into the parenthesis. So I'm going to go second entry so I can get the whole thing back. I'm going to scooch over. So it's 1 minus 0.5. That's what's nice about my calculator in the second entry. And boom, I get 4,147 rounded up. It said round up to the nearest integer. So I rounded it up to the nearest integer into the problem. Okay, so this first one right here would definitely be 4148. I'll let you do the rest of them. I'll give you a second to do those, to stall the video, and then I'm just going to write the answers down for you so that you can know what those values are. So the first one, I like the blue one. So it was 4148, rounded to the nearest whole number. Nearest integer, sorry, is 2401 is what I would get, 2401. And the last one, 1692. And those are using the same formulas. The only difference is because the z value changed, then my z star value changed. So for this one, you would have used 1.96 for your z value. And for this one, you would have used 1.645 for your z-value. Okay, let's move. So in hypothesis testing, last part of this, last thing we have to do for this section. Hypothesis testing, we want to distribute the sample proportion, the null hypothesis. Remember the null hypothesis, nothing is going on, okay? So at H of O, our p-value is going to become what we call p sub O, okay? We're just going to use different notation to have that discussion with that. The standard error, going right back to the formula we've been using today, we're going to take p times 1 minus p divided by n, but now we're going to replace p with p sub O, okay? In other words, the null hypothesis is going to take over for the best point statistic. So when we test for a single proportion, what we call a standardized test statistic, and again, I want to bring light to this so you don't freak out about this. When we look at our line we've been working on here today, single proportion, confidence interval level, we already did it today, but now look, now we're in a testing statistic environment. We are actually testing to see what is going on with something. We seek evidence over here. Over here, we look for a range. Well, here's the formula that we're going to work through right now. In order to find a z number, we're going to take a p hat minus a p sub O. Remember, that's the null. We're going to divide by the root of p sub O times 1 minus p sub O divided by n. And the reason we're doing this is p hat is the sample statistic, p sub O is the null, and the standard error calculation is what we've already been using today. Now, it is important, obviously, that our n values are greater than 10. Okay, and I do need to move this up a little bit because it says the area of the tails in the standard normal beyond z. Remember, this is all about having a p-value and rejecting a null or not rejecting a null value. So let's look at our first one here. Actually, our only one here, I think. Question number 24. It says, use the normal distribution and given sample results to complete the test of the given hypothesis. Assume that the results come from a random sample and use a 5% significance level. So we have some really important information here. First of all, p sub O is 0.2. So that right there becomes a very important statistic to us. P sub O is 0.2. Okay? Change over and make that important. The alternative, two-tail. We have a not equal to 0.2. We have a p hat value. So we actually have a statistic of 0.2. And we have an n value of 995. Okay, so what we first of all want is a test statistic. Remember that a test statistic value is a z number. Okay, when we say a test statistic, we are talking about a z value. Go to the formula sheet and go find your statistic, and the z number is equal to p hat minus p sub O divided by root of p sub O times 1 minus p sub O divided by n. It's more writing than it actually is calculating. We have a p hat number. We have a 0.25, comes from the problem, minus the null hypothesis, 0.2, divided by the root of, again, the null hypothesis, 0.2, multiplied by 1 minus 0.2, divided by n, and in our problem, n was 995. Go do the math. Give you a second to get that done. Put it in your calculator. 3.94. Remember, that's our z number. That's our test statistic itself. I'm going to write that into here. 3.94. As we study z values more, you'll understand how extreme that number is because it's more than 3 standard deviations. Matter of fact, almost 4 standard deviations to there. Now, it wants us to get a p-value. And we could use a p-value from computer, but I'm going to use our calculator. So I'm going to go to my calc, And in my calc, remember, I'm calculating area here. Okay, I want to know the area of 394 going right. Let me draw that out for you for a second. I now know that on a normal distribution with 0 being the center, I have a 3.94 z-value right here. I want to know how much area is consumed on a 394 as extreme as 394. Well, in my calculator function, that will be normal CDF. That's area function. And we will calculate that normal CDF based on 394 as our lowest number, going to a maximum number, and I will use E99, positive 1, E99. So I bring up my calculator. I go to my normal CDF, number 2. I put in my low number at 3.94. That's my low cutoff. My upper cutoff is 1 E99. And it's always a 0 and a 1, always, because I'm on a z-test. And look how tiny this thing is. This thing is 4.075, 4.07, actually 0.76, E negative 6, which means take this thing and move it this way 6 times, which is 0.0000, 1, 2, 3, 4, 5, 4076. Well, remember that our alpha level was 0.05. This is so much smaller than this that we will have no conclusion but to reject the null hypothesis with very, very strong evidence. I'm going to move over. I'm going to get over to my writing skills here. My p-value, 0.12345, right? 0.76. But now I'm going to add something here because remember, this was a two-tail. So I'm going to tell you that because it's a two-tail, we have to multiply it by 2, because we do. And it did say to round our decimal to 3 places here. So I'm just kind of doing the math for you here. I'm multiplying by 2 because it's two-tail. This is how much was on one tail. And when I round that answer to 3 decimal places, guess what I'm going to get? A big fat 0. So what will I do? I will reject. Why will I reject? Because the p-value is very strong, or my evidence is very strong against the null hypothesis. That is chapter 6.1. Please email me if you have any questions at all. Enjoy.